All right, welcome. Over the next few minutes, we're going to take these awesome, kind of messy, handwritten notes about statistics and probability, and we're going to turn them into a story that just makes sense. Let's get right into it.
You know the feeling, right? You're staring at a page full of data, and it's like trying to read a secret code. It just feels like this big, overwhelming wall of digits.
I mean, look at this. These are the test scores for 20 students, straight from the source notes. As it is, it's just a jumble. Can you tell who did great or who might need some help? What's the average score? Nope, not at a glance. And that's exactly the problem that statistics was designed to fix. And this really hits the nail on the head. Just like the notes say, statistics is our toolbox. It helps us wrangle all that numerical chaos and turn it into something clear, something useful, so we can make way smarter choices.
So how do we actually start telling that story with the data? Well, the very first step, always, is to bring some order to the madness. We've got to organize things before we can see what's really going on.
So, the first tool we're pulling out is called a frequency distribution. Now, don't let the fancy name fool you. It's really simple. Think of it like this. You've got a giant pile of laundry. You're just sorting it into bins, one for shirts, one for socks. You get the idea. We're just doing the exact same thing, but with numbers.
And just like that, check it out. We took those same student scores and we grouped them into ranges. How many kids scored between 50 and 59? How many in the 60s? All of a sudden, a picture starts to form. You can see right away that most students landed somewhere in that 60 to 79 range. The chaos is already starting to make sense.
Okay, so our data's organized. Now we can ask the next big question. What's the typical score here? We're basically looking for the data's center of gravity. And for that, we've got three main tools in our belt.
First up is the one we all learned in school, the arithmetic mean. You probably just call it the average. You just add everything up, divide by how many numbers you have, and boom. It's like finding the perfect balance point for your entire data set.
And here it is, the classic formula, pulled right from the original notes. That funky E-looking thing, that's sigma, a Greek letter that just means add everything up. So you add up all the values and divide by n, which is just how many values you have. Simple, right? But incredibly powerful.
Our next tool is the median. Now this isn't about the balance point, it's about the physical middle. If you line up every single number from smallest to largest, the median is the one sitting right in the center of the line. But, and this is the part everyone forgets, you have to put them in order first. That's the key. This example from the notes is perfect. It shows what to do when you have an even number of data points, so there's no single middle number. Easy. You just grab the two in the middle, add them up, and divide by 2, and there you have it, a perfect median of 20.
And our third tool for finding the center is the mode. Honestly, this one's the easiest of the bunch. It's just the number that shows up the most often. That's it. If you own a shoe store, you're not interested in the average shoe size. You want to know the mode, so you know which size to stock up on.
So which one should you use? Well, that's the million-dollar question. The mean is fantastic when your data is pretty evenly spread out. But let's say a billionaire walks into a coffee shop. The mean income of everyone in that shop would suddenly be millions of dollars, right? That's misleading. In that case, the median is your best friend because it isn't yanked around by those extreme outliers. And the mode? Perfect for when you just need to know what's most popular. Knowing which tool to grab for the job, that's the real skill.
So we can find the center. Awesome. But that's only half the story. Think about it. Are all the numbers clustered tightly around that center, or are they scattered all over the map? We need a way to measure the data's personality, its spread.
The word for this is dispersion. It's all about consistency. Imagine two basketball players who both average 20 points a game. One of them scores exactly 20 points every single night. The other scores 40 one night and 0 the next. See? Same average, but totally different dispersion. One is reliable, the other is unpredictable.
And the number one tool we use to measure this is the standard deviation. Think of it like a special ruler for measuring variability. It boils everything down to a single number that tells you, on average, how far each data point is from the center. A small standard deviation means your data is consistent and predictable. A big one means it's all over the place. Okay, now I know this formula looks a little scary with that sigma again and the square root sign, but don't let it psych you out. All it's really doing, step by step, is measuring the distance of every single point from the average. It's just a super precise method to get that one really meaningful number.
All right, let's switch gears. Up until now, we've been talking about describing data we already have, but what if we want to figure out the chances of something happening in the future?
For that, we need to jump from statistics into the world of probability. And it all begins with a wild tool for counting huge numbers without actually counting them.
And that tool is the factorial. You'll know it by the exclamation point. This little guy is the fundamental building block for almost everything that comes next. The factorial of a number, say 5 factorial, is just 5 times 4 times 3 times 2 times 1.
And this is where your mind is going to be blown. You might think 10 factorial, how big could that be? Well, get this. When you multiply 10 by 9 by 8 all the way down, the answer is over 3.6 million. That is the incredible power of factorials. They let us see how many ways there are to arrange things, and that number gets massive fast.
Okay, that brings us to the two heavyweights of counting possibilities: permutations and combinations. They sound similar, but they answer different questions. And the entire difference between them boils down to one simple but absolutely critical question. Does the order matter?
Here's the deal. In a permutation, the order is everything. Your phone passcode 123 is totally different from 321, right? But in a combination, order is completely irrelevant. If you're picking pizza toppings, pepperoni, mushroom, and onion is the exact same pizza as onion, pepperoni, and mushroom. The end result is the same. And these examples from the notes make it crystal clear. On the left, a license plate with the letters A, B, and C is a permutation, because ABC is a different plate than CBA. The order creates a unique result. But on the right, connecting points A, B, and C to make a triangle is a combination. It doesn't matter what order you connect them in, you get the exact same triangle every time.
So take a look at this number, almost 2.6 million. What do you suppose that represents? It's the answer to a very famous combination problem.
That's it. That's the total number of different 5-card poker hands you can possibly get from a standard 52-card deck. It's a combination because it doesn't matter what order the dealer gives you the cards, your hand is your hand, and because of the tools we just talked about, you now get the logic behind calculating a number that big. So that makes you think, doesn't it? What other possibilities in your world could you start to figure out now?